Hi folks, this is Linear Algebra Take Home 7. We're given a linear transformation between the polynomials of degree 2 or less, given by this. We're asked to find the eigenvalues of t and a basis for each of the corresponding eigenspaces. Prove t is diagonalizable, and find a basis for P2, which produces a diagonal matrix representation. Okay, so there's a lot to do. And we're going to get at this using, of course, a standard matrix representation for t. So I'm going to use the basis we've been using all along, t squared, t, and 1. Let's look at where t squared goes. A is 1, b and c are 0. So this goes to negative 11t squared plus 16t plus 8 t of t, b is 1, a and c are 0, negative 8t squared plus 13t plus 8, and t of 1, a and b are 0, c is 1, I get 4t squared minus 8t minus 7. So I'm going to get a matrix representation for t. Negative 11, 16, 8, negative 8, 13, 8, and 4, negative 8, negative 7. And that's going from the standard basis to the standard basis. So now the game is find the eigenvalues for this, find the basis for the eigenspaces for this, and then what they correspond to back here in P2. Okay, so the first step is to find the eigenvalues. We take the determinant of m minus lambda I, which is the determinant of, you just subtract lambda off the diagonal. Now, there's no real advantage to expanding along any one particular row or column because we don't have a lot of zeros there. You go through the usual expansion. When everything settles down, you should get 9 minus 3 lambda minus 5 lambda squared minus lambda cubed. Now we set this equal to 0. You've got lambda cubed plus 5 lambda squared plus 3 lambda minus 9 equals 0. And you can go through your rational zeros theorem and synthetic division nonsense, and you'll be able to factor it down to lambda minus 1 times lambda plus 3 quantity squared equals 0, which gives us lambda equals 1 and lambda equals negative 3. Now this is where things could go awry for us, because the lambda equals negative 3 eigenvalue is of algebraic multiplicity 2. So in order for t to be diagonalizable, we need to get an eigenspace here with dimension 2. Okay, so let's go looking for those eigenspaces. We'll start off with lambda equals 1, and so really we're looking for the null space of m minus 1i. We're asked to solve this equation, so we're looking for the null space of this matrix here. Okay, so we look at m minus 1i, and we're going to just subtract 1 off the diagonal here of m. So negative 12, negative 8, 4, 16, 12, negative 8, 8, 8, negative 8. And technically we have an augmented matrix with a bunch of zeros on the other side. So that's not going to affect anything, but we'll go ahead and put those in for completeness here. We'll put this into reduced row echelon form and see what we get out of it. Alright, so after you go through the usual row operations, you get this as your reduced row echelon form. And so we get our solution x, which is the unknowns x1, x2, x3, we've got x1 plus x3 is 0. We've got x2 minus 2x3 is 0, and 0 equals 0. This means that the x3 is free, so we get one free variable, which we knew we would get at least one. So we get x1 is negative x3, x2 is 2x3, so our solution x is x1, x2, x3, so it'll be minus x3, 2x3, x3, which would be x3 times negative 1, 2, 1. So, if x is an eigenvector corresponding to lambda equals 1, then x has to be a multiple of this vector. So this is a basis for this eigenspace. Okay, so the question is, what does that correspond to? Negative 1, 2, 1 corresponds to the polynomial negative t squared plus 2t plus 1. So for E1, a basis for this space is this polynomial. Okay, now we're going to go look for a basis for E negative 3. That's the eigenspace corresponding to the eigenvalue E equals negative 3. And so we're going to look for solutions to m plus 3i, x equals 0. And so I'm going to be adding 3, because we're subtracting negative 3, we're adding 3 to the diagonal. So it'd be negative 8, 4, 16, 16, negative 8, 8, 8, negative 4. Oops, and once again, we're technically solving a homogeneous system of equations. So I'll add that column of zeros. And now I'll go do the reduced row echelon form of this matrix. Alright, so you go through row operations, and here's the reduced row echelon form of this matrix. So as before, if I take this out of the matrix, I've got x1 plus x2 minus a half x3 is 0, and then the last two equations come out as 0 equals 0 and 0 equals 0. This tells me that the x2 and the x3 are free, which is what I want. I want two free variables because lambda equal negative 3 was an eigenvalue of algebraic multiplicity negative 2. So if I look at my solution x, which as always is x1, x2, and x3, if I solve this for x1, I get negative x2 plus a half x3. I have 1x2 and 1x3, and I break this up. To the x2 part, I get negative 1, 1, 0, plus the x3 part, which is 1 half, 0, 1. So any solution to this equation is in the span of these two vectors. These two vectors are linearly independent because I have a 1 here but a 0 there, and I've got a 0 here and a 1 here. So these two vectors then constitute a basis for this eigenspace. Alright, so the column vector negative 1, 1, 0, since we are using the standard basis of t squared t1, corresponds to the polynomial negative t squared plus t. Likewise, this corresponds to the polynomial 1 half t squared plus 1. So together, a basis for E negative 3 is these two guys. So I put this together with my basis for E1, and I get a basis for P2 is negative t squared plus 2t plus 1. That was the basis of E1, and then I add these two in. So these guys were the basis for E negative 3. And we proved a theorem in class that eigenvectors that correspond to different eigenvalues are linearly independent, and so I'm guaranteed then this is going to be a basis for P2 because I have 3 linearly independent vectors in a 3-dimensional space.